Okay, let's try to continue this video sections. In this video, we will discuss the last topic from this point cloud video series. In this video, we will discuss one of the popular applications, which is generative model in the point cloud data domain. In particular, I select this paper, DiffFacto, from ICCV 2023, because I find that this paper is very interesting. It gives us control ability to control the result of the generated point cloud. For example, we can control the style of the shape, and also we can control the size of the generated result. Let's start with discussing the motivations of this work. So with the recent advancement in the 3D point cloud generations, there still lack an effective way to control the generation result. And then this paper, the name is DiffFacto. It proposed a vectorized representations with cross diffusions. So this name is from this one, diffusion, diff, and also facto from vectorize here. That allows for control in both part style and also the transformations. And in this case, the transformations consist of the position, which is the translations, and also the size or scale. Let's see some of the use case here. We have the input chair like this. We can sample different style of this particular part here. In this case, it's the leg. We can sample into another style. For example, like this style. We sample another leg style. We can have this different style. Another sample like this and another sample like this. So this is part level sampling. We basically sample different style for every part. And then another one is we can sample the configurations. Configuration here refers to this transformation, which is the positions and also the size. In this case, we can sample also in every part. Like here, we sample a short back of the chair. Here, the back of the chair, we have the higher, but the leg, we have the shorter than this one. And then in another chair here, we have a thin, but we have the higher leg here, and we have the kind of a normal but small seat and also the back. We can sample these configurations in every part here. And then another use case is the part mixing. We can mix by taking the style of the arm from here and also the seat from this second chair, but we take the style of the back and also the leg of the chair from the chair one here. And this is the mix of these two chair here. We can do this by using this DiffFacto method here. And then another use case, we can do interpolations. We can interpolate, for example, here we can interpolate the back of the chair, interpolate this chair 1 with this chair 2 here. And this is the interpolation result, the blue one here. We can see that in the right side here, this close to this style, and then in the left side here, this close to this style here. But the remaining parts are the same with this style. Because we only interpolate the back of the chair here. Yeah, this is some of the controllability that we can have by using this DiffFacto method here. I think this is a very interesting of the generative method in the point cloud data domain. And let's see the high-level idea of this method first. So to achieve this controllability, they decompose into two aspects. The first aspect is the part style. This is an aspect that we can control the style of the part. And then another aspect is the transformations, which is the size of the part for every shape here. Okay, so after we have this, which is the latent variable representing the style of the part, and we have this is the latent variable representing the size of the shape, we can use these two as the conditional input to the diffusion network to generate this original chair here. In high level, the whole pipeline here, we will learn the style and also the size in the dataset. So we will learn the distributions of the style and also distributions of the size, the transformations that are available in the dataset. And later we can generate our own shape by using different style of the part and also different size of the part here. And let's start to discuss every detail in this every block here. The first is the part stylizer here, the first block, how we can achieve this latent variable that can control the style of this part. First, we have the original part here, and we decompose into independent part because in the dataset we have the part label. So one of the requirements of this method, we need to have the part label so that we can decompose into independent part here. And after this, we can do the canonicalizations. We have discussed the canonicalizations in this video playlist. If you are not familiar, you can refer to that. But in short, we want to transform for every part here to be in the same pose. But because of this dataset, they already have in the same pose. We don't need to do that. And another one is we need to transform into the same scale. And the third one, we need to transform into the same origin, which is the origin here is 0, 0 here. Okay, so we will do canonicalizations for every part here. Transform to the same scale and also into the same origin. And then after we have the canonicalized for every part here, we will compute the global feature here, latent variable, with the embedding dimension 256 here. We use the PointNet-like encoder. We also already discussed in this video series. If you are not familiar, you can review the previous video section. And then in the upper part, we also want to compute a latent variable, but in this case, we sample from Gaussian noise here. And later we will align these two. This is latent variable. This is latent variable. But this latent variable in upper level here, we sample from the Gaussian noise. In the lower part here, we directly estimate from the original canonicalized part, right? By aligning these two, by using this KL divergence, minimizing this loss, we ask that this generated latent variable, either from this and this are well aligned. So later we can just use either this or this. It can generate the same result. Okay, and then in particular, this method, they use this CNF, continuous normalizing flow. One of the property in CNF is we can do inverse operation here. In this case, if we have the output here, we can do the inverse operations to retrieve the input. This is very useful later when we do the part interpolations. For example, if we want to interpolate this back to this back of another chair, we can compute this here, compute this latent variable. We also compute this latent variable here. We have 1, 2 from chair 1 and chair 2 here. And here we can inverse to get the input, right? Because we already aligned these two here. We treat these two are the similar. And then we inverse, we get the corresponding input from chair 1 and chair 2 here. Chair 1 and chair 2. And then we just do the interpolation. We interpolate these two input here, interpolation. For example, we just take the middle. You can apply your weighting value based on your interpolations. And then after we get the interpolated result in this input space, we can compute again the interpolated latent variable here by inputting this interpolated input here to this CNF. And later, the output of the interpolated input here, we can use to generate the final shape output. It looks like this. Yeah, so this is the reason why they use this CNF. If you want to know more detail, you can read this paper from NeoRIPS 2018. Okay, so next we will discuss the second block, which is the transformation sampler. The transformation sampler, it consists of C. C here is the translation. We have the X, Y, Z translations, and also scale. Scale also we have 3, correspond to the axis X, Y, and also Z. To learn this, we will do fitting the transformation C and S to the transformation mapping from the canonical to the original part here. When we do this canonicalization, we have the S head here, and this is the original. We can multiply with the original scale that we use in the canonicalization plus the translation C. And this is the ground truth, right? So here we have the ground truth, and also we have the transformation that we want to estimate. So basically, we will estimate this and minimize with the corresponding ground truth here, S and C, that we use in the beginning when we do this canonicalizations here. We minimize this using L2 norm here. And in particular, we here use the log scale here. If we draw the log scale, we have something like this. In this case, we put more range into the lower scale value here. We have the higher range, but in the higher scale here, we only have a very little range here, because probably in our dataset we don't have the high scale shape, because probably most of the dataset we only have this range of the scale. So that's why here we use the log scale. And then if we think more, the valid transformation is not only one, right? We can have a multiple transformations, I mean multiple scale and multiple translations that can generate a valid shape. For example, if we have a chair like this scale, high chair here, this is a valid chair. We can also have the short chair like this, for example, with the same style. This is also valid. So the number of valid transformations can be multiple, not only single. If we only fit into the single transformations that are available in the dataset, it will be overfitting. And also in the generative model, we usually refer this as mode collapse. So instead, we will sample multiple transformations by inputting this Gaussian noise here. To get this transformation here, this is the T network. The input will be in the Z for every latent here, because the transformation is associated with the every part here. And also YK here. YK is we sample from these distributions, and we sample number of K. Let's say we sample 5, 0, 1, 2, 4 here for 5 sample. And this is the corresponding ground truth. We compute the distance by using this formula. And we see which YK here that minimize this L fit. Let's say for this particular sample 1, the one that minimized is from the Y2. So we use this, and we fit this Y2 into the ground truth in the dataset. And later, if we have the sample 2 here, and we also sample another 5 YK here. And let's say in this particular sample 2, the one that minimized is the last YK. So we will fit this YK using this one, and so on and so forth. Again, in high level, we do not want to fit a single combination of a transformation in the dataset, but we acknowledge that, oh, there are multiple valid transformations, and we only fit one of them to the dataset to avoid this overfitting and mode collapse. So basically, this is the detail of this transformation sampler. And let's next discuss the third block, which is the denoising network. Okay. In the diffusion method, we have the original sample, and we will gradually apply some noise, right? We apply small noise to here, we apply noise to here, we apply noise to here. We do this in different timestamp. This is the timestamp 0, correspond to the original, timestamp t, and so on and so forth. For example, we have like 1000 timestamp. And in the diffusion network, it will convert into unit Gaussian with the mean 0 and the variance is 1. And then later, we will denoise it, removing the noise that we add before. We gradually recover into the original shape here. So this is the high level of the diffusion network. And in this paper, to achieve this diffusion network, they use L cross attention layer. CA corresponds to the cross attention with the number of L layers here. And the query and also the key and value specified by what I write here. So the input of the query is the concatenations of the here. XT here is the noise in the timestamp t. Here, the noise here. The shape of the noise will be the number of point. For example, 2048 by 3 for the XYZ. And then J here corresponds to the index of the part here, like part 1, part 2, 3, and so on and so forth. And then the T here is the transformations, which is the shift and also the scale here. This is the query. And then the key and the value, we use the Z, which is from here, part style latent here. And then we also concatenate with the transformations here, concatenate with the semantic index J here, and also the timestamp number here. Later we will recover the noise in every timestamp until finally we achieve the timestamp 0 correspond to the original input here. To recover this from noise to the original input here, in diffusion network, we will estimate the noise here. Given the network, which is this cross attentions, we will estimate the noise in the particular timestamp. This is the cross attention network. Cross attention network, we have the query and key value input here to estimate the noise. And this is the corresponding ground truth noise. Because when we apply the forward noise here in the diffusion, we know this ground truth noise, right? Because we give a little by little noise in the forward process. So we have here the ground truth. And we try to estimate this noise. And later we can recover from this noise into the original shape here. Yeah, so I think this is the third component, which is the diffusion network. And one that is special from this paper, in the forward process, diffusion network, usually it will convert into the unit Gaussian, which means that the mean is 0 and the variance is 1 here. But in this paper, they prove the mathematical formula, you can check in their paper, that because we model these reconstructions from the canonicalized part here into the original shape here, we involve the transformation. In this case is shift and also the scale. In this case, they propose a forward process here. Instead of convert into unit Gaussian, it will convert into Gaussian with the mean is the shift of these transformations and the variance is the scale of this transformation. Yeah, so this is one of the difference of this paper to the general diffusion network that's converted to unit Gaussian. Yeah, I think that's it for the overall pipeline. And let's see the experimental result, how we can generate the different style of the output here. First, we can sample a selected part and then keeping the rest. For example, if we have this chair, we want to keep this back and also the seat here. And we want to sample only the leg. We can do something like this. Here we apply this back. The back is here. we compute the corresponding latent. We have this one. We also compute the seed here. We get the corresponding latent variable here, right? And then we sample the lag by sampling here. From the unit Gaussian, we get the corresponding latent variable, right? So we have three for the back, seed, and also lag. In the query key value in the cross-attention diffusion here, we can give the corresponding semantic, right? J here is the label of the semantic. The corresponding latent variable of the lag, we put the J is the label of the lag. So this is how we can generate different style of the lag of the chair here. And again, we sample again another latent variable for another lag, and we do again to generate this original chair. So in this case, we have the different style of the lag here. We can also actually sample another part, not only single part. For example, if we want to keep this, the seed, and we want to sample different style of the back and also the leg, we can sample here one for the back and another one for the leg. And later, the Z here, when we input into this cross attention, the Z here, we just basically give different semantic label J here. For example, 0 is for back, and then the seed is 1, for example, and the leg is 2. You can just give the corresponding label to this J here when we compute this cross attention to generate this vinyl shape here. And this is the first way we can sample one of the part or several parts to generate the shape. And then next, we can also generate the transformation. In this case here, if we want to generate the transformation, we use the same style. Here we compute the corresponding latent variable, and also on the seed here we compute the corresponding latent variable. But instead of using the ground truth of the transformations, like in the previous one here, when we generate this, we use the ground truth shift and scale correspond to the canonicalization this. Instead, we will sample new transformations by sampling this Gaussian noise here. We input to this to generate another transformations, and this is transformation 1, this is transformation 2, this is transformation 3, and so on and so forth here. Later, we use this sample transformations and also the original part style as the input of this diffusion network. And this is another result for another category: airplane, lamp, and car here. And then another different approach that we can generate is we can do the interpolation. Let's say we want to interpolate the back only here of the chair. We can compute this. Back is this. We compute the corresponding latent variable for the chair 1, and this we compute the same for the chair 2, and this correspond to this one because we already aligned by using KL divergence, chair 1, chair 2, and we do the inverse. We have this ability because of this normalizing flow here. We have the input correspond to the chair 1 and chair 2, and in this chair 1 and chair 2 we do the interpolation, and the interpolated result we compute back the corresponding part style latent here, and we can use this to generate the shape, and this is the interpolation result. And then next we can also do mixing here. For example, I want to generate a chair with the style of back from this chair 3 and the leg for the chair 2, and then this from the chair 1. So basically we can just apply this, compute this, we have the corresponding part style, this compute, we have the corresponding part style, this also compute latent variable, and we use this 3 latent variable, We use the ground truth of the transformation if we want to use the same transformation, or we can also sample for different size of the shape. We can use this as the input of this diffusion network, and finally we have this result, which is the combinations of these three styles here. And this paper try to compare with the existing method, and we see that this paper have a much better result than the existing method. I think that's all for this video sections, and see you in the next video. In the video conclusion here, we try to conclude and summarize this video series here that we have discussed 6 important papers in the point cloud data domain.